Let's take a look at an example. In this example, we want to find our peak time, percent overshoot, settling time, and rise time for some transfer function g of s, which is given below. As always, I would encourage you all to pause the video and try to work this problem, or at least set it up by yourself, and then come back and watch the video to see the solution. So the first thing that we want to do is we want to find our omega n and our zeta. And so we can do that directly from our g of s, of course, but our g of s, we can get our a and our b terms. So remember, this term here multiplied by s in the denominator is going to be our a. So we can say a is 15. And our b, remember, for our b and as well as our omega n, we always want to use this denominator term because sometimes if we don't have unity gain, this term will be different. In this case, we do have unity gain, so we could use either of those two to get that our b is equal to 100. So a is 15 and b is equal to 100. So what we can do then is use equations we had found previously that relate our zeta and omega n to a and b. So we find that our zeta is equal to a divided by 2 root b. Plugging in, we have 15 divided by 2 times 10, which gives us 0.75 for our damping ratio. So as expected, remember we're talking about, in these previous videos, we were talking about underdamped response when we talked about all these parameters. And for our system to have an underdamped response, we need our damping ratio between 0 and 1. And so as expected, our damping ratio is between 0 and 1. Now our omega n, remember, is simply just the square root of b. So square root of 100 is going to give us 10 radians per second for our omega n. Okay, so now we can start finding these 4 items that we were looking for. So for our peak time, and so for 3 of these, we're essentially just going to plug into the equations we had sort of derived before. So for our peak time, we have pi in the numerator. We have our frequency of 10, and then that's multiplied by the square root of 1 minus zeta squared. So our zeta is 0.75 squared. And plugging that in, we get a peak time of approximately 0.475 seconds. Okay, so now for our percent overshoot, so percent OS, we have that's equal to the exponential. So writing that a little different than what we've seen before, I've got exp as opposed to e, and then actually having a superscript. So this is going to make it a little easier to fit and be legible. So we have negative zeta times pi in the numerator, where our zeta is 0.75, and then divided by the square root of that 1 minus zeta squared. And again, our zeta is 0.75. And remember, our percent overshoot is only dependent on that zeta term. We multiply that by 100 to make it a percent, and we get that this is approximately 2.838%. So that's our percent overshoot. Okay, moving on, we can then do our settling time. If we use our more generalized approximation, we just have a 4 in the numerator. I don't have it written in the notes for this example, but we could use that more detailed equation to get something a little more precise if needed. In the denominator, we have our zeta times omega n, so 0.75 times 10. And so that gives us approximately 0.533 seconds. Okay, so for these first 3, it's pretty straightforward. We're just literally plugging our values into the equations from the previous videos. But for our rise time, it's not quite as straightforward because we're not just plugging into a value. So what we want to do is we want to use our data that I mentioned in the previous video. And so this comes from figure 4.16 on page 150. And so I have confirmed that is the correct figure in the 8th edition, and that is the correct page number as well. And so what we have in this table is for various damping ratios in this left column, we have normalized rise times in the right column. So the key word here is that these are normalized to frequency. So if you were to look at the plot, instead of just a time, it's been normalized to an omega sub n times the time. And so we'll see how we deal with that here in a second. So in this case, we know that we have a 0.75 for our damping ratio. So we found that up here. So obviously there's not a 0.75 entry, if we want, we could of course go and make a program to sort of analyze and compute this with more resolution, but maybe we don't need that much precision here. So what we can do is say, well, our 0.75 is in between these two entries. So what we could do is we could do linear interpolation to figure out an approximate value for our normalized rise time. So doing that linear interpolation, we can see that our damping ratio of 0.75 corresponds to a normalized rise time. So let's call it TR norm of approximately 2.3. And if you have questions about how to do this linear interpolation, let me know and I'll be happy to go over that. So this is our normalized rise time though, and in the problem statement we're just asked for the rise time. So what we need to do to get that from our normalized time to our rise time is just divide by our frequency. So TR norm divided by the omega n, which is going to be approximately 2.3 that we got from our linear interpolation, divided by our frequency of 10, and that gives us 0.23 seconds. Now we can kind of do a sanity check with some of these numbers, knowing the relationships between the various things. Of course, our rise time should be becoming before our peak, so it should be less than our peak time, and we see that's the case. Our peak time is 0.475, our rise time is 0.23, and then of course our settling time should be longer than both of those, and we see that it is at 0.533 seconds. So one quick thing, or a couple quick comments I want to make, is that notice we were able to characterize the behavior of this system in our frequency domain from this g of s transfer function equation. So if we didn't have the equations that we had derived previously for our TP, percent overshoot, TS, and this data for our rise time, what we would have had to done is we would have had to take our inverse Laplace transform. So inverse Laplace transform. Then we would have had to plot the response. So that would have given us our g of s, or sorry, not our g of s, that would have given us our c of t. So plot response. And then we would have had to take measurements from that plot. So of course, this is a lot more work than what we did in this example here, and so that again is just to kind of highlight the benefit of having these equations and being able to solve these things directly from our transfer function in the frequency domain.